1 minute. Hi everyone, welcome to Machine Learning with Python as part of our study circle. And our expert Jamie Wasawa will continue with the advanced machine learning topic. And we look forward to hearing from him. I know it's a little bit of a rain in the west coast of India, but definitely Jamie is able to present. So welcome everyone, and I will hand over to Jamie. Jamie, go ahead, speak. Thank you.
So thank you for the introduction, sir, and welcome everyone for the machine learning with Python. The topic that we'll be continuing will be advanced machine learning 6.2. So,
Yeah, Agnivesh, I will text you.
so today's session will cover the advanced regression models. So let's get started with this. So today we'll be reusing the data set that we have already discussed in past few videos or sessions for covering different topic. So the same data set will be used in this one as well. So this is the IPL data set that we have used first. You can see the categories that there are, or the columns, or the features, then the data types those respective features have, and the description. The one thing that I want you to keep in mind are the data types that these contain. There are continuous and categorical both. As for categorical data types, we'll be converting them into one hot encoding with the get dummies, as this is a linear regression model. So when we read the data set and look its info, and this is what the information about the data set looks like. It has 130 entries starting from 0 to 129, 26 total columns. The data types that contain and that the data set contains is a float, int, and object. Objects are nothing but the categorical data types. Then the memory usage regarding it. Just printing few of the records from the data set, and just giving you an example of what the columns are and what the entries about those columns look like. And these are the columns that will, or these are the features that we will be using in order to predict the sold price or the selling price of the, or the auctioned price of the players. So first we'll be using the, or making the X features. So as I told you to keep in mind about the categorical features, those categorical features have to be transformed into the, have to be one hot encoded, because we are using a linear regression model, and linear regression models does not take categorical features. So we we one hot encode them, and using the pandas get dummies function, and store them into IPL auction encoded DF or data frame. So this is what we are doing. First, we created X features where we took all the columns, then created the DF, encoded DF, and you can see the encoded DF when they are printed with the IPL auction encoded DF columns. These are the encoded DF, and that was created. So that will become our X feature, and Y will be our IPL auction DF, the column from column sold price from the IPL auction DF. So now we'll be standardizing the values of X and Y. Why do we standardize it? Because we want the values that are collected in the X and Y features. These features have to come under one scale in order to have a fair comparison. So we'll be standardizing the values of X and Y, uh, which is also called as a normalizing the scale, or bringing the X and Y values under one scale. So this can be done by subtracting mean from the values and dividing by the standard deviation of the feature or variable. The standard scalar function of scikit-learn dot pre-processing package provides this functionality. So we'll be using that functionality. We first import that from scikit-learn, then initialize the X scalar, name it X scalar, and use the standard scalar. Then using the X scalar or for fit transform on X and giving it the name of X scaled. And for Y, we'll be simply using the Y minus mean of Y divided by the standard deviation of it. So we have standardized the values of X and Y. Now we'll be splitting the data set into train and test. The train and test, we have used scikit-learn's model selection train test split. So we are splitting the X train, X test, Y train, Y test in a 80-20 ratio with a random seed of 42. Then for building the model, we use the scikit-learn.linear and linear model and import the linear regression from it. We'll store it under linreg and fit the model with X and Y's train split. And when we get the output of it, you can see uh, the output for a linear regression. The copy X basically means that it does not create a if when it's true copy X, it simply means that it will create a copy of X, and on them the modifications will happen. So it does not modify the original data. Then fit intercept, it's basically an intercept line passing through it. If it's false, it will be through origin. If it's true, it will pass through and fit through the data and have a intercept line through it. The number of jobs is nothing but the parallel jobs that are needed to be done. Here we are just doing this, so it's a 1, and normalize is simply meaning that normalize the values of them. So we this is the output for the linreg fit. Now for getting the coefficients, and this you can see the array that we get, and you can see that there are a bunch of numbers, and some of them have the minus sign or the negative sign before them, and some are positive signs. The negative and the positive sign shows the effects of the player's sold price or the selling price of the player. So we'll be creating a data frame which will have 2 columns to store feature name and the corresponding coefficient value. So basically creating a coefficient a column name and with its respective coefficient value, and sorting the feature by coefficient value in a descending order so that we get the highest ones first. Then when we try to plot these coefficient values onto a bar plot to see the magnitude of the values that indicate the effect on the sold price. So so you can see the code that generates the plot, and when we see the plot on the right, you can see the average ODI runs and sixers are the most influential features that affect the selling price of the or the auction price of the player. And if you can see that age 2 and age 3 are some of the features that are negatively affecting it, the price of the player. But apart from that, you can also see that test runs and high scores, HS and T runs for test runs and a high score for HS. These are the values that should actually positively impact the player, but are shown as negatively impacting it. This can be due to multicollinearity. So let's see uh, how to address it. So first, we'll be calculating the root mean square error, and we will be doing that with the help of a get train test RMSE method. That will be a custom method that will be creating, and which will take a model as an input and compare the price of the train data split and the test data split of the model and its performance on the train data split and the test data split. So we define the function called get train test RMSE, then get the y predictions of the model, get the get get the root mean square index and round it up, then get the test predictions of the model, and then in the end printing or yeah in the end printing the models train and test scores. So for the Lindrig model that we have created, you can see that we are getting the 0.679 and 0.749 score. Now whenever we try to calculate and get the score, we expect similar numbers in terms of scores, and this is not the similar number that we expect. So the score should be similar on train and test and should be due to overfitting due to the training data. Overfitting occurs when a model learns to capture noise or random fluctuations in the training data rather than underlying pattern, leading to poor performance on unseen data. Using simpler models or regularization are some of the ways to deal with overfitting. So, so let's see regularization as a solution to overfitting. So what does a regularization does? It helps us to get in control of the coefficients, highly inflated values, and keep them from getting inflated. So when there is a overfitting, it is observed that it's typically caused by the inflation of the coefficients. To avoid overfitting, the coefficients should be regulated by penalizing potential inflation of coefficients. A regularization applies penalties on parameters if they inflate to large values and keeps them from being weighed too heavily. The regularization involves adding a penalty term to the loss function during training, which discourages the model from fitting the data too closely. Basically, overfitting happens when it is not able to generalize the new data. So, regularization helps us by penalizing the model or adding a penalty term onto the model while training the model to its loss function, which discourages the model from fitting the training data too closely. The two types of regularization methods that we'll be using is lasso, which is a least absolute shrinkage and selection operator, and which is also called as L1, and L2 regularization, which is called as ridge regularization. So starting with lasso or L1 regularization, the penalty term that it uses is an absolute value of the coefficients of the features, which it encourages the sparsity in the model, meaning it tends to force the coefficients of less important features to be exactly zero, effectively removing features from the model. So epsilon MSE equals to 1 by n. N is nothing but the number of records. The summation of I equals to 1 to n, where starting with a yi minus beta 0 plus beta 1 x1 till beta n xn whole square plus alpha, which is a multiplier, and its summation with a beta I for I equals to 0 to n, the mod value of beta I. Then for regularization, L2 regularization, which is also called as Ridge, the penalty term in this case is the sum of the square of the coefficients of the features, which discourages the larger weights of the coefficients and leading the model to a more balanced weights across all the features and reducing the impact of the outliers. So in this case, our error term becomes a 1 by n summation of I equals to 1 to n y minus beta 0 plus beta 1 x1 till beta n xn whole square plus alpha into summation of I equals to 1 to n for beta I square. So let's see their applications of applying them and how to apply them for our model. So ridge term distributes a ridge term, which is L2 regularization, distributes the coefficients values across all the features. Lasso seems to reduce some of the coefficients to zero. Features with coefficient value as zero can be treated as features with no contribution to the model. Basically meaning that if coefficients are zero, they can be said as they are least significant, and because they are least significant, they can be removed as well, which in turn it reduces the number of features that the model has to work with, and therefore Lasso also works as a feature selection technique. So applying the L1 and L2 regularization on our model, starting with rich regression, you can see that we are using the scikit-learn's linear model to provide the ridge regression for our model. The ridge regression of a scikit-learn takes two parameters. One is the alpha's value, which is a float data type, is the regularization strength. Regularization strength must be a positive float, which improves the estimation of the parameters and reduces the variance of the estimates. Larger values of alpha imply stronger regularization. Then maximum iteration is the second parameter that it takes, which is a integer data type, which is the maximum number of iterations for the gradient solver. So when we start with scikit-learn's a linear model to import a ridge from it, and we are basically naming it our model ridge and fit it for the training y and x and y is a train split, and passing the values for the ridge for our model, the maximum iterations and the alpha value of 1, the and then getting the score for our train and test through the custom method that we made, which was a get train test RMSE. The values that we get are 0.68 and 0.724, which has a reduced gap from before for 0.679 and 0.74 were the previous values. This is the present value that we are getting through ridge regression. So as we have tried the alpha equals to 1 as our value, now we will pass alpha equals to 2. And you remember that regularization gets stronger with larger values. So now trying it with alpha value 2, and the values that we get are 0.682 and 0.706, which gets more closer, or the gap is more reduced now. So for the time, this alpha value is working for us, and this is the alpha value that will be continue with. Now we'll discuss the Lasso regression, which, like the ridge regression, uses two parameters: the alpha value, which is a float, which is of float data types, which multiplies the L1 term. Default value is set to 1, and the maximum number of iterations for the gradient solver. So similarly, using the scikit-learn's linear model to import Lasso, then using Lasso for our X and Y's train split, and then using the Lasso on the alpha value of 0.01, and passing that model to the get train test RMSE method that we created, which is our custom method. The values that we get are 0.688 for train and test 0.698. So this from the scores, we can say that the model is not overfitting, and we can use the lasso to remove the least significant features by using a data frame and filtering out the features with zero coefficient. For the lasso, I already mentioned that it works as a feature selection method, because it basically gets the value of coefficient which are less significant to 0. So storing the values of the columns that have are least significant or are of zero coefficients, and then printing the values of those columns. These are the columns that we get as an output. You can see the image on the bottom right, the coefficients that have 0, and the columns: T wickets, ODI, strike rate, batting, average bowling, then playing role, bowler. Now that was Lasso. Now we'll discuss elastic net regression. Elastic net combines both the ridge and the lasso, and it works with both of them, and gives us a single way to uh, measure our model's capability. So with ElasticNet, you don't have to choose between these two models, and because the ElasticNet uses both L1, L2, and the L1 penalty. So the error term becomes 1 by n summation of yi, summation of I equals to 1 to n, yi minus beta 0 plus beta 1 x1 till beta n xn whole square, plus gamma, which is basically the L1 or the lasso hyperparameter, into summation of I equals to 1 to I equals to 0 to n for the mod value of beta I, plus sigma, which is the L2 hyperparameter or the ridge parameter, which is the summation of I equals to 1 to n for beta I square. So the elastic net takes the two parameters, which is alpha. Alpha is basically sigma plus gamma, and the second parameter that it takes is L1 ratio. You can see the mathematical representation of L1 ratio, which is gamma divided by sigma plus gamma, or gamma divided by alpha. And the value of alpha is 1 by default, and the L1 ratio lies between 0 to 1. So when we take the gamma value of 0.01 and sigma value of 1, our alpha value is 1.01 and L1 ratio gets to 0.0099. So using these values for our elastic net model and then passing that to the custom method of get train test RMSE, we are getting the value of 0.789 and the test value of 0.665, which kind of makes the scores worse. So we'll be sticking to the Lasso, which is the L1 regularization model, which gave us the best uh, scores for the models that we have trained. So now to just summarize what we have done for our session today. We started with advanced regression models and we used the IPL dataset. We imported pandas, read the dataset, and got the information of the dataset using .info. You can see the information that it has, the number of entries, and number of columns, and kind of data types, and the memory usage that it has. Then we used X features, and we converted the categorical features into the one-hot encoded DF using the get dummies of pandas. Then the encoded columns, you can see the encoded columns that we created are these. Then we created the X and Y values, standardize those values to get them into a single scale or a normalized scale using this, where we use the scikit-learn's standard scaler for X, but for Y we simply use Y dot mean and Y standard deviation for creating its normalized value. Then we split the data set for train and test for X and Y. We built the linear regression model for the training data splits of X and Y. Then we printed the coefficients of the linear regression that we created. These are the values of it. Some are negative values, some are positive values, showing us the impact of the coefficients on the selling price of the auction price of the players. And then we created a single data frame containing two columns to store the values of the columns and to store the values of the features and their respective coefficients. And we used those coefficient values to plot the bar plot. This is the bar plot that we got, and you can see that average ODI runs, average bowling are the positive impact on the player's selling price, and the age, if you see on the y-axis on the bottom, the age are being the negative impact on the player's selling price. Whereas you can see that high scores, HS, and test runs, T runs, are negatively impacting the selling price according to the model, which should not be the case but it's being so because of the multicollinearity. So we'll be calculating the root mean square error. We used the get train test RMSE model. We defined that model which takes we defined that method and which takes a model as an input and gives the output for its train and the test run. So for our Linrig model, this is the score that we get, and it has a gap, and it does not have a similar score, which we are actually expecting. So this is due to overfitting. So to solve overfitting, there are two ways: use a simpler model or use a regularization. So using the regularization, starting with ridge regularization for our model, we use the ridge using the linear model of scikit-learn. Then getting the ridge model into the train test, get train test, and these are the scores that we get for alpha value equals to 1. For alpha value equals to 2, these are the scores that we get, which is a kind of an improvement compared to before. And now moving to lasso regression, which is a type of regularization. We start with this, and we start with the value of alpha value of 0.01 and maximum iteration of 500. This is and when we pass the model to the get train test of the root mean square error, these are the values that we get. So lasso regression is also used for feature selection. So we will be creating a data frame for our coefficients for columns and the respective coefficients. And when we get the coefficient for value equals to 0, these are the values that we get. The lasso score is really good and has similar scores. Now we'll be using the elastic net regression, which takes two parameters, which is alpha and L1 ratio. You can see the alpha, which is basically sigma plus gamma, and L1 ratio is gamma divided by alpha plus sigma. Sorry. L1 ratio is gamma divided by sigma plus gamma. So following those formula and these values, we train our elastic net or eNet model and pass it to the get train test method, and these are the scores that we get. And as mentioned before, the elastic net model gets worse scores, so we'll be sticking to the lasso score, which is getting or giving us the similar values and giving us good results. So yeah, this is it for this today's session, and further we'll be continuing with advanced machine learning algorithms. So thanks a lot for listening, and thank you so much.
Thank you, Jamie, for the presentation. I think Aditya had some questions. I answered him on the chat window. So
Sure,
we can close today's call and hope to see you on Wednesday.
sure.
We will jointly meet and over the presentation, we'll take care of the remaining. Okay, for the
Yeah,
next.
sure.
Thank you, Ramit.
Thank you.
And
Thank you.
thanks a lot, Jamie. I appreciate your time. Let
Thank
me
you.
just end the record.